Okay, we got to get started or I won't be able to get you to lunch on time. You don't want to be last. I was last and the line is very long. So I can see that there are more questions that come when I show applications. I wish in hindsight that I'd spend a little less time on theory and more on applications, but I can't change the past. I like to tell my students, we can't change the past. We made a mistake, we got to move on. So that's the way it is. So one of my big interests is in studying reaction chemistry of combustion. And so I bring together my interest in lasers and spectroscopy and my interest in combustion chemistry to study combustion chemistry using a shock tube. So I've been working with shock tubes now for a very long time. And a shock tube is a great way to study combustion chemistry. We can generate any temperature you want, any pressure you want, in a controlled way. So there will be some people here, I hope, who care a little bit about combustion chemistry. And maybe a few people who care. Is there anyone here who cares about shock tubes? Oh, good. One person. Great. Okay, so we use shock tubes as a controlled reactor. And I'm going to give you a little bit of background about lasers and shock tubes together. So I'm going to give you an introduction to shock tubes, and then I'm going to show you some representative applications with vibration relaxation, ignition studies, and some ideas about modeling. So shock tube is usually a long, constant diameter tube separated into two chambers, high pressure chamber and a low pressure chamber. It's a photograph of one of the shock tubes in my laboratory. They tend to be about 100 diameters long, so this device might be 35 feet or so, something like that. This would be the end that's not shown here, and that's where all the measurements are made. Okay, so this is basically an introduction to the shock tubes for those of you who aren't familiar with them. This dividing thing is typically called a diaphragm if you're using a diaphragm shock tube instead of a diaphragmless shock tube, which is being undertaken by one person here. So this pressure difference across the high pressure gas and low pressure test gas is enough to break this diaphragm, and a shock wave moves down this, shock wave is formed, typically is formed in about 10 diameters. It moves at a nearly constant speed, then it begins to gradually slow down. We measure the rate of progress with some pressure transducers on the sides. When the shock wave reaches the end, let's see if this does this, yes, when it reaches the end, it reflects and moves back, and that's called the reflected shock wave, or region 5, where the gas is stagnated. So the boundary condition here is that the gas velocity is 0. So basically the velocity is stagnant in this region. We send laser light through, and then we use absorption to detect the species and temperature versus time that might occur. So the thing about the shock wave is it's nearly planar. It's thin, maybe 10 meter paths. And so it essentially gives us a step change in the translational temperature, followed quickly by the rotational temperature and more slowly by the vibrational temperature and the chemical change. So we're interested in this region here. And we can produce essentially any temperature that you want. So the advantage is that if we make an accurate measurement of speed, we can get a very accurate measurement of temperature. If we measure this speed to maybe 0.1%, we know the initial temperature in this region to maybe 0.5%, which is pretty amazing at the temperatures that we work at. We have shock tubes that cover a wide range. We sometimes go down to 600 degrees. This says 4,000, but I've got one student who's working at 8,000 degrees. We're working typically between about a third of an atmosphere and maybe 100, but we have capabilities to cover this wide range. And I've done experiments when I was your age that were down at around 0.1 torr. So it's possible to work at really low pressures as well. But this is history, and so I'm kind of interested in this history. I've been around the history a long time. So the first shock tube was apparently made around the year 1900, I believe, in France by VA. Excuse my French. About the time of the Second World War, people became very interested in shock waves, mine safety, aerodynamics, and saw the potential of shock tubes for producing controlled high enthalpy gas samples, which could be expanded to achieve high speed flows. To my knowledge, the first time anyone used a shock tube to study chemistry was either at Caltech or in Canada. I'm not quite sure which, but it was early 50s, about 60 years ago. Into the 60s, there was a lot of interest in using shock tubes to study planetary entry. In fact, that's how I got interested in shock tubes. They were interested in studying what happens for a vehicle entering the atmosphere of, I think it was Jupiter. Anyway, the entry speed was something like 20 kilometers per second. So the idea was you could use a certain kind of a shock tube to produce the enthalpies that corresponded to that extreme environment with very high temperatures. It was around 1970 when the lasers first became applied to shock tubes for species detection. And I was one of those people that did that. Since then, there's been quite a few applications. People interested in astrophysics, nuclear explosions, chemical kinetics, aerodynamics, heat transfer, a lot of different things. So it's just basically a way of getting controlled, temporary, high temperature, and possibly high pressure source of gas. Actually, it can also be an aerosol, but mostly we deal with gases. So if you've had a course in gas dynamics, you know that we'll think of the shock wave as a planar discontinuity. It moves at a constant speed, and once you know that speed and you know the conditions of the gas into which it's coming, pressure, temperature, usually you'd have to know the composition, you can calculate the conditions on the backside. And if it's a gas with constant specific heat gamma, you can calculate for the initial high pressure region P4 and the test gas pressure P1, you can calculate the properties of this device. When the shock wave reflects, you come back, you can also calculate very accurately these conditions here. Velocity is 0, and you can calculate the so-called P5, T5, rho 5 properties this way. You can do this for a constant gamma ideal gas, or you can do it for a real gas. When we go to really high conditions of, say, 300 atmospheres, we use an improved equation of state. So there's different ways of solving the problem, but the shock wave theory is well known. A reference book for this is by Gaydon and Hurl. It's about 60 years old. There's a lot of books on shock waves at about that period in time. Just to show you what we can do for, say, gas like air with a gamma of 7/5, if you produce a shock wave of Mach number of 7, pressure jump across the incident shock is 50. There's an additional pressure jump of 7, so taken together, pressure jump is 350 from the initial pressure to region 5. The incident shock temperature is about, say, 2700 Kelvin, and then another 2.2, so you can get up to extremely high temperatures rather easily. Now, what's the downside? Well, this only lasts for a short length of time. You may only get 2 milliseconds of test time. In fact, when we were working at NASA Ames, 1960s, we had like 10 microseconds of test time because the conditions were so extreme. But now we've learned, and I'm going to show you here in this lecture or the next one, that we can get up to tens of milliseconds of test time. So these are just plots that show how rapidly the temperatures change with Mach number. So we're getting numbers here. This is T over T1 or T5 over. You can get up to, here's like 50, 60. You can get incredibly high temperatures with the shock wave. So sometimes a shock wave is characterized by what's called an XT diagram. So this is the coordinate X, this is the location of the diaphragm, here's the end wall, here's the test location typically. So this is ideal theory. This is not exactly correct, but this is the ideal theory for a shock wave. At time 0, you assume that the diaphragm is removed instantaneously. That pressure difference forms a shock wave that moves at a constant speed. It means the line is a straight slope. It doesn't actually happen quite that way. It takes 10 diameters to form, and then it slows down a little bit due to friction. Going to the left is the leading edge of an expansion wave, which moves at the speed of sound into that test gas. The boundary between the test gas here and the driver gas here is this region right here. And then this blue region is the region of the gas that's been heated by the incident shock wave. So this is the gas in region 1 that's been processed by the shock wave. Now what happens here is the reflected shock comes back and goes through this test gas and heats it again. And so we're really interested in this region right here. Once this reflected shock hits this interface, waves come back and end your test time unless you play a trick, which I'm going to show you. So a typical situation might be, this is really out of focus, but I apologize for that. This is the relative pressure, and so in time in microseconds. So you see here's a little step That's when the incident shock wave goes by right here on the way from left to right. It goes to here, and then the reflected shock comes back, and now the pressure stays constant for, in this case, 1 millisecond. Then there's some wave that takes place due to this, and it comes back, and that means your experiment is over. So if you only want to do an experiment at less than 1 millisecond, okay. If you want to go longer, you have to pay attention to this problem. So it's easy to generate a few milliseconds of pretty good test time. Here's a case where we use tailoring. That means we control the composition of the driver gas so that we get acoustic matching between the test gas and the driver gas. In that case, there's no wave reflection. In that case, we get rid of this termination of the test time, and we get longer test time. So this is what we get if we do this tailoring. It's not perfect, but now we're out to 9 milliseconds. And in fact, in other experiments, we're out to, our world record is 100 milliseconds. So with tailoring of the composition, you can get times of the order of 10 milliseconds. And the pressure, the constancy of the pressure implies a constancy of the temperature, which we care about for purposes of chemistry. Okay, so we've talked about temperature. And usually temperature is defined, meaning that the molecules are distributed over the available quantum states by Boltzmann statistics. There's the translational, also known as kinetic temperature of the gas that's associated with their motion. There's the internal degrees of freedom, which have temperatures, and that would be the rotational temperature, the vibrational temperature, and the electronic temperature. In equilibrium, there's one temperature. But you can create situations in which there are two temperatures, one for the vibrations and one for the translations and rotations, and we can watch how long it takes for the vibrational temperature to reach its final equilibrium value. That's called vibrational relaxation. And so I think it's interesting to show you how we can study this phenomenon. You're now familiar with this diagram, which is the parabolic energy, potential energy for a simple harmonic oscillator, where we have the energy is parabolic because the energy is 1/2 kx squared, where k is the spring constant, fundamental frequency that we got from the spring. The reality is that it's not exactly harmonic. It's harmonic at the bottom, and then it becomes anharmonic on the attractive side and on the repulsive side. But the main thing to take away is that these energy levels are quantized, and the spacing for vibration is much larger than for rotation, and so the vibrational temperature takes longer to develop because it happens by means of energetic collisions, which have to bring in enough energy to take the molecule from here to here to here. So it takes longer in terms of collisions. Boltzmann statistics tell us how the molecules will be distributed over the available quantum states by this simple relationship, where we use, for in the case of the partition function for vibration of a diatomic molecule, it has this form, 1/1 minus e to the minus theta v over t. So when we have theta v, that's h nu over k, or hc over k, which is my number of 1.44 times the frequency in wave number units. So if you go to Hertzberg and you look up omega E, and it's 2,000 degrees, which is approximately right for most molecules, a lot of molecules, then that means the characteristic temperature is 2880. So that's statistical mechanics. So we can plot the populations for vibration. Here's vibrational level 0, 1, 2, 3, 4. And at room temperature, we would have all the molecules here and virtually none down here. These are drawn as continuous lines, but in reality, there's only points along a line. As you go up in temperature, then the distribution adjusts, and some molecules begin to form at higher V's and come down at lower V's. So the slope of this line changes with temperature. And so if we could measure a few points on this line, we can measure the temperature of that energy mode. And we can watch it adjust until it finally reaches the same value as the rotations and the translations. So remember, temperature is defined for that energy mode if the molecules obey Boltzmann statistics. And in many cases they do. And eventually, non-equilibrium processes always drive towards equilibrium. So if you wait long enough, you'll always achieve equilibrium. But how long does it take? Well, we can't get that from thermodynamics. We have to do that from kinetics, physical chemistry. So we characterize the transfer of energy from the kinetic energy into the vibrational mode. It's called VT energy transfer. So we have some molecules that are not excited vibrationally. How do they get excited? They undergo high-speed collisions because the temperature is high. High-speed collisions which provide a transfer of kinetic energy to vibration. That's called vibration translation energy transfer. And that rate of change, the rate of change of vibrational energy, is given by a very famous Bethe-Teller equation, came from around 1950 probably, that says that the rate of change is proportional to the difference between the equilibrium value that would apply at translational temperature and the current vibrational energy over tau. This is what's called a relaxation equation, in contrast with a kinetic rate equation. This is a relaxation equation that just says the rate of change of this property is proportional to the difference between its value and equilibrium over tau, and tau has the physics. Tau is related to the collision frequency and the probability of energy transfer in a collision. This characteristic time was found by Bethe or Teller to be of this form, where the time is 1 over ZMP. Forget this term. Z is the collision frequency per unit density. M is the density of colliders. So this is really a collision frequency times the probability of a molecule going from V equals 1 to V equals 0 in that collision at that temperature. So that's the fundamental quantity right there. That's the rate coefficient. Per unit density, there's the density. So, and I won't say how this equation was derived, but it was based upon a simple harmonic oscillator model. So, so the question is, how can we measure tau? How can we measure tau? That's the fundamental quantity we'd like to have. So let me illustrate this with this diagram. So let's imagine we have temperature versus time, and we're sitting here before the arrival of the incident shock wave, and all temperatures are equal, room temperature. The shock wave arrives, and the translational temperature jumps up within a couple of collision times. And the collision time, collision frequency in the room right now of a nitrogen molecule is about 10 to the 9th, 10 to the 10th per second. So in a time of the order of 10 to the minus 9 seconds, this temperature of translation is defined and jumps up. But the vibrations require a lot more energy, and it takes a lot more collisions in order to adjust. But if we wait long enough, we'd see that the vibrational temperature would evolve and equal the translational temperature. But because of conservation of energy, the translational temperature goes down and the vibrational temperature goes up. Now the reflected shock comes back and it does it again. Temperature goes way up, and then the translational temperature comes down while the vibrational temperature comes up. So that's what we think happens. And the question is, how long does it take? If you wanted to model supersonic flow over a high enthalpy flow over a body, as might occur in, say, planetary entry, you have to have some sense as to how long does it take for this to occur in order to calculate something like the heat transfer to the vehicle or the radiative emission from the high temperature gases. So that's the idea. And so the question might be, how do we measure these times in the laboratory to test the theories that are developed by the theorists? And so the time is going to be shorter when the temperature is higher, because it has to do with how fast do collisions occur with have enough energy to convert vibrational quantum number by 1. So you have to come together with enough kinetic energy to equal the vibrational energy. And at high temperatures, there's a greater frequency of high energy collisions. So that characteristic time right here will be shorter than the one down here. So this is what was done by some famous researchers, Millikan and White, back around, probably around 1960, maybe 55. And so they measured the characteristic times tau, and they're usually plotted as p tau because tau is inverse with pressure. So they do it in atmosphere second units. And here's some results for pure nitrogen, and here's temperature up here. Pure nitrogen, and here's nitrogen in air, and here's pure oxygen. And the theory tells us that we should plot this as 1 over t to the 1/3. In that case, the theory says the data should fall on a straight line. I won't go into that theory. So people were interested in this, and they measured it in the laboratory to constrain the theorists who were trying to figure out what these numbers should be. The techniques that people used in 1964, Millikan and White, the techniques that people used in those days were based upon interferometry mostly. So this is essentially before the invention of the laser. So they would take a snapshot of the density distribution across the incident shock wave. So think of the shock wave as proceeding from left to right, and we capture a picture right when the shock wave is right here, and these are lines of density. Density is constant, and then the density jumps, then the density increases further as the temperature goes down. So temperature is going down because the energy transfer from kinetic energy to vibrational energy causes that temperature to go down and the density to go up. These are called fringes. So this was a measurement. This is an interferometry-based scheme. You measure this fringe shift in a characteristic time over which it evolves, and you can infer tau. So that's a density-based optical system for measuring these characteristic times and seeing what they are. So for example, if you had 2,000 degrees, and if you had 1 atmosphere, the time is 1 millisecond. On the other hand, if you did that over here with pure oxygen at 2,000 degrees, you'd be down here at about 10 microseconds. So why is oxygen faster than nitrogen? Because the vibrational energy spacing is smaller, much smaller. Characteristic temperature for vibration of oxygen is about 2,000. Characteristic for temperature for nitrogen is about 3,000. So what's a modern experiment? So we undertook this study recently, well, about 3 years ago, I guess, to try to study this at high temperatures and to see if we could do a much better job of the data. We used a strategy of heating the oxygen in argon. And the reason is that argon has a gamma of 5/3. If we have a heat bath, then the temperature is more nearly constant. And we're going to use a laser technique. It's based upon a laser called a MIRA to measure O2, and we're going to do this in the deep ultraviolet, looking at the spectra of the type I showed you yesterday, I guess, rho vibronic spectra at short wavelengths in the ultraviolet. This is what the experiment looks like. This is a very complex. This is about $250,000 laser, actually. Very expensive. My most expensive laser. There's a pump laser which goes into this cavity, which produces light at about 900 nanometers, and then it's converted into shorter wavelengths, say 211, by this process. This laser pulses at 80 megahertz, and each pulse is about 2 picoseconds long. So it's a burst of short pulses. But we use Beer's law, and now we're going to use cross-section. So fractional transmission is E⁻ the number density, but we're going to probe a specific vibrational quantum number. We're going to probe a specific transition, and we're going to try to measure, and we're going to, knowing the cross-section, we're going to look at the rate of change of this absorbance and infer time. Now, if we've measured the number density in a specific quantum state, or 2, we can infer the temperature if we assume that it's a Boltzmann distribution. So the hypothesis is that the vibrational distribution obeys Boltzmann statistics, but its temperature is changing with time. So that's a hypothesis that we have to test. So here's the MIRA. We can work it over a wide wavelength range. It pulses at 80 megahertz. It's fast enough that we think of it as a continuous wave laser. It puts out a couple of milliwatts in this wavelength range. So the question is, how does this relate to the vibrational population? So if we were to plot band strength or cross-section for different vibrational quantum numbers versus wavelength at a given temperature of 2,500 degrees to be represented. So these are the absorptions that would occur in different vibrational quantum numbers. This is a continuous curve, but in fact, point by point along this line are the different rotational transitions. Each wavelength would correspond to a specific vibrational level and multiple rotational states because they're closely dense. So basically, we have a laser that can be tuned at different specific colors. Each one is sensitive mostly to a specific vibrational quantum number. That's the basic idea. here's what a result would look like. So we're measuring absorbance, which is the exponential quantity. That's the negative log of I over I0. And it varies from, here it is at here's the room temperature gas. And we're measuring this probably for V prime, double prime of about 4. So 211, let's see, which one was that? 211. 211 is mostly sensitive to V double prime of 4. This is a logarithmic plot. So we're measuring at that wavelength versus time, and we're taking the negative log and we're plotting it versus time. Data are the black line, and the red is the simulation. This is at 1200 Kelvin, and a certain amount of oxygen and argon, 1 atmosphere, 15 centimeter path. So basically what you can tell, what the experimentalists would look for and say, what is the noise level in absorbance units? And it's like 0.3%, that's good. So we have a very high resolution measurement of the evolution of time of the population in a given vibrational level. And we can take those numbers and convert them to relaxation times and plot them on the so-called Landau-Teller diagram. I should have said that diagram of p tau versus t to the minus 1/3 is called Landau-Teller, because Landau is the one who figured out it should be plotted versus t to the minus 1/3. The good news is that these data points for oxygen and argon are have very good precision, very low scatter. The bad news is we got the same answer as Millikan and White, who used interferometry 50 years ago. Those are smart guys. So they got some good answers, and we basically get agreement. So if we go into pure oxygen, we get a little discrepancy there and a slightly different number than they did. So anyway, that's the state of the art for measuring vibrational relaxation of a diatomic molecule. I just wanted to do that because it kind of emphasizes what we think of as temperature. Now let's go to chemistry, where there's just usually one temperature involved. And I want to talk about a few different kinds of examples of how we can use shock tubes to study chemistry. So if you've had a combustion course, or maybe even in the chemistry course here by Professor Wong, you would know that we think about the hydrogen-oxygen system as being characterized by a set of reactions. A set of reactions. We might call it a mechanism. And in that system where we start with hydrogen and oxygen, the question is, how do they evolve to produce water? And this will be represented by a set of reactions or a mechanism, of which the important ones are shown here. And if you had another course, or maybe Professor Wong's course, you would know that the reaction which is usually rate limiting in terms of predicting the rate of combustion or ignition or explosion of hydrogen-oxygen mixtures is this one right here. It's so-called most important reaction in combustion chemistry. Takes one reactive radical and produces two. So these have names. This one initiates and produces a radical. This one propagates the number of radicals 1 to 1. This one branches the number of radicals. 1 goes to 2, 1 goes to 2. This terminates radicals and removes them. Those are called termination. So there's different classifications of these reactions. Your mechanism then would require, you have to specify the reactions, and you've got to specify the rate coefficients, and you have to specify the thermochemistry. That would constitute everything you need to know to predict the evolution of species in a combustion experiment. Progress is made over time in specifying what the reactions are, getting in better and better thermochemistry, and then finally getting the rate coefficients. The rate coefficients are the hardest things to get. They can be calculated theoretically, but for the most part, we rely on experiment. Experiments are still quite a bit better than the theory for most categories. So again, you might be getting this from Professor Wong if you're taking this part. The radicals are the key to understanding how chemistry proceeds. We're not so sure actually how the very first radical is formed, but it turns out that the mechanism by which it's formed isn't as critical as the behavior of the radicals once they build up to a certain minimal level. So this buildup is really determined by these radicals. And if you take these three reactions together, typically they're shown in a plot like this, which says, I start with 1H, and because of the interaction between all four of these steps, it's as if 1H instantly becomes 3H's. So it's explosive. Every time 1H becomes 3, 3 becomes 9, 9 becomes 27, and it happens so fast that that's called ignition. And it turns out that therefore this reaction is the dominant one. The effect is to go from 1 radical to 3, but the rate at which that happens is dominated by the rate at which this reaction takes place. So it turns out to be really important. Now, a crude measurement, which we still do, is called ignition delay time. The engineers would like to know, well, if I put together a mixture of hydrogen and oxygen at some temperature and some pressure, how long before it ignites? How long before it explodes? And we can do that experiment in our shock tube. Here's a measurement of pressure. So in this mixture. So it's 94% argon. We observe, here's room temperature or pressure. Here's the jump in pressure at the incident shock. It looks like it's about an atmosphere. Here's the jump in pressure at the reflected shock. And now here's the period in which we watch the gas. And then suddenly at 170 microseconds, pressure goes up. That's the way we would determine the ignition delay time, it's called, which the engine people care about, using a pressure signal. We might also look at the emission of chemiluminescent emission from OH. And that's another way to measure the ignition delay time, and you get the same number. So there's different ways of measuring the ignition delay time, which is the single number that the engine designers want to know, because you have to control that within if it's a reciprocating engine, it has to be in the right time frame. So we could get this ignition delay time different ways, by pressure, by chemiluminescent emission, and so on. But we don't learn very much about the details of the chemistry. You'd really like to study it in more detail, and that's when we use lasers. Nonetheless, we still do some work in which we characterize the ignition delay time. Now it's plotted versus 1/T. It's called an Arrhenius diagram, because the reaction rate theory says that the rate coefficients and therefore the ignition delay time should fall roughly on a straight line when plotted on a semi-log plot versus 1/T. So one question is, how does the ignition delay time vary if we change the fuel within the category of N-alkanes, the normal alkanes? So some theorists would say, well, it's all the same. In this high temperature region above 1250 and up, they would say that all of the alkanes are about the same. But if you do really careful experiments, you can show that as you go from a C4 molecule to a C5 up to a C9, that there is a slight decrease in the delay time simply because the bonds break a little easier for the C9 than for the C4. But roughly speaking, they do fall on more or less a common line for the normal alkanes when plotted this way. If you go to lower temperatures, now dropping down all the way down to say 700 degrees, and now we're looking at somewhat higher pressure, 15 instead of 2 atmospheres. Same kind of plot, ignition delay time versus 1/T, and we're looking now at heptane, C7, versus endodecane here, C12, in air. These are in air, and these were in oxygen. You can find that this, what was a straight line, turns over, and then starts to go down, and then goes up. That's called the NTC region. So again, if you're in the chemistry course, Professor Wong's probably talked about this. Negative temperature coefficient. This is a positive temperature coefficient. When it turns over and goes flat or goes down, that's called the negative temperature coefficient regime, and then it goes positive again. And so obviously, the type of chemistry that's taking place here changes. When you get below 1,000 degrees, something new is happening that causes the reactions to change. So instead of continuing up, there's a regime in which new chemical reactions come into play. The mechanism has to be adjusted to explain this. And this is a region of current interest. How and why does this happen? Can we measure this precisely? Can we understand this effect? Because the chemistry needed to explain this is different than the chemistry needed to explain this, and so on. So we can think of this as an interesting current issue. Okay. That's a little bit of background on this. I want to spend some time talking about advances in shock tube methods. So I told you that they were first used for chemistry around 1950s, 65 years ago, 60 years ago. The geometries haven't really changed that much, but some of what's really changed is the instrumentation, the availability of computers for control and recording of data. That's changed a lot, but the gas dynamic equations haven't changed. So there's it's about 5 inches internal diameter. Here's the diaphragm section. One of the things we've done is instead of having this fixed length driver, we've added to length and we've made a U-tube to make the effective length longer. And you'll see why in a bit. Here's a picture of the middle part of the shock tube with a lot of valves and so on. And there's the end wall where we make all of our measurements. And this is a blown up view of the test section of our high pressure shock tube, which shows some of the instrumentation we use. So I'm going to talk a little bit about how we've advanced shock tubes in the last 5, 10 years to make them. What do we want to do? We want to achieve longer test times. We want to achieve more constant reaction conditions. And we want to be able to model the events that take place in this environment. Because as you'll see, it's not exact, it has some issues about how to model the thermodynamics of the situation. It's not a constant volume reactor, what is it? It's something in between, and we have to figure that out to do the modeling. So a conventional shock tube would give us, say, 1 to 3 milliseconds of test time, and we might plot that time here. So this is this is milliseconds here. So this would be 1 millisecond, 10 milliseconds. So it's not that hard to get to 1 to 3 milliseconds of test time independent of temperature. So roughly speaking, this is our operating envelope for our unmodified shock tube. We get down to 5 microseconds or so, up to maybe 2, 3 milliseconds, independent of temperature. This line is the simulated ignition delay time for endodecane in air at 10 atmospheres. So you can see we can't quite get to this region that's really interesting right now for people who are trying to design new types of engines and to model the behavior of the chemistry in those engines. This is the region, rough approximate region of people who use rapid compression machines. Rapid compression machines are a little bit like a piston. The piston is accelerated and tries to compress the gas in a chamber, and then the piston kind of slows down, and so it's not an instantaneous heating. It's isentropic compression to some peak pressure, and then what happens typically is the pressure declines because of heat transfer to the sidewall. So in a rapid compression machine, instead of having a step change in pressure, you get a gradual change in pressure followed by a gradual decay. So it's a different kind of a device. It's typically used between about 10 and maybe 150 milliseconds. And it's also a little bit outside the most interesting regime, but they can access this part. We want to modify our shock tube. So the latest design we have allows us to get up to about here. Our record so far is 100 milliseconds at about 550 Kelvin. My goal is to access this thing. My goal is to I could say the goal is to eliminate the need for rapid compression machines, but there might be somebody here who likes rapid compression machines. Is there anybody doing rapid compression machine? Okay, okay. So,
wait for like 2 more years.
Yes. But in any case, there's always value in having duplication of experiments. You learn something when the data don't agree. You learn something and you make experiments better. So there's a good, and rapid compression machine has its role. But the idea is to get into this regime of chemistry and where we can compare methods and try to advance. By the way, flow reactor, I should have changed this to be flow reactors. Flow reactors also work between maybe 10 milliseconds and longer. They mix the gases. There's a problem with flow reactors is when's time zero. Even with the rapid compression machine, when's time zero? There's no time zero, but you usually take the peak of the pressure and call that time zero. So that's okay, but you have to model. I always say experiments are always right, but you have to model them the right way. So we use this driver extension and some tailoring ideas, and with that, those changes we can get up into here. There's another problem. And these are kind of small problems, but they become important when you try to do things better and better. If you do an experiment in, say, propane and oxygen, equivalence ratio of 0.5, this would be 1,000 degrees Kelvin, and you measure pressure, what you would see is there's this jump in pressure, and in your mind, you'd like to think that the pressure is constant. But in reality, the pressure always seems to grow linearly. We call that the DPDT problem. And we've tracked that down to be associated with the gradual attenuation of the instant shock wave. So because the instant shock wave is slowing down, the post-shock pressure P5 gradually goes up with time. And we can account for that with some theory, but we don't like it. Because if the pressure is changing with time, and then we get the ignition delay over here, when we watch, there's the observed pressure, there's a contact surface bump. That means we did not do the tailoring perfectly. We did it well, but we didn't do it perfectly. If we'd done it perfectly, this would have been a straight line. And now it goes bang. So that's the ignition delay time we observed in this experiment. The people who model it usually assume that the temperature is constant, but the temperature is not constant. And that's the reality. So we call this the DPDT problem. And the fact is, if the pressure is varying by 3% for every millisecond, the temperature is varying by 1.2%. And 1.2% of temperature, this would be now 12, there's a 12% change in temperature here. 12% change in temperature is a huge change in the ignition delay time. It's so sensitive. So what are we going to do about that? You can try to model it, which people now at least try to account for this in their model. But you have to measure this. You have to measure this and report it in your paper so the modelers can try to put that in there. So we've tried to make the problem go away. The boundary layers cause this problem, and so we have redesigned our shock tube. We call this a driver insert, so that the area is no longer constant. And with this design, we can achieve this. So we can make the pressure nearly constant. Get rid of this problem, and what happens? The ignition delay time goes up by 40%. So they're both correct, but if you're going to model it, it's much easier to model this experiment than it is this one. If I repeat this experiment, we might get slightly different DPDT. You'd have to report it so that every experiment would have to be modeled. This one we can say is nearly isothermal, and then ignition delay. So we're gradually trying to make the quality of the data better by improving the experimental apparatus, which will make the life simpler for the modelers. The modelers will usually adjust their models to fit your data, but if they use the wrong gas dynamic model, then they're going to get the wrong kinetics conclusions, and that's the problem. That has been the problem. We're getting better and better at this. Here's the difference that it makes. If we look at this propane case, here's some data that we took. Actually, these are some data that came from somewhere in Europe. They had a small diameter shock tube, and so their DPDT was huge, 12% per millisecond. There's the data for the ignition delay time that they observed. These points here are what we get in our shock tube, which is larger diameter. That's the ones with the kind of green turquoise inside. That's what we get. Same mixture using our shock tube with DPDTs in this range. Here's the data that we get if we fix our shock tube. So remember, all the data sets are correct, but you're going to get a different conclusion if you don't take this gas dynamics problem into account. So the idea is to try to make the experiments better so that the models are more appropriate. So we might call this the constant volume limit of this experiment. So it's higher quality data, therefore. And so experimentalists now should always monitor this DPDT. Is it nearly zero? How big is it? And we need to report that in our experiments. Okay, there's another problem. So gradually you solve problems and you go on to the next problem. This is a gas dynamics problem. It's really a fluid mechanics problem. Turns out that these reflected shock reactions are not really constant volume or constant P. And I'll show you this here. Let's look at a case of heptane ignition. We like heptane because the chemical mechanism is pretty well developed for heptane. People believe in it. They think it's nearly correct. So here's what we would see if we do in a conventional experiment in the shock tube with 0.4% heptane, equivalence ratio of 1, a lot of argon. So it's actually a dilute experiment, which tend to be better. When we have a gamma 5/3, the shock tube behaves better. 1400 Kelvin, 2 atmospheres. Here's the time of ignition delay right here. Looks pretty good experiment, nice constant pressure. That's because these times are only 300 microseconds. So if the shock tube is less than a millisecond, it's a pretty good device without any modification. But how would you model this? If you say I'm going to model it as a constant pressure process, you could model it as constant pressure up to here, but it is not constant pressure afterwards. So if you want to model the combustion chemistry that takes place during and following ignition, you can't assume constant pressure. Then they'll say, well, let's assume constant volume. Yeah, but it's not constant volume either. If I do my simulation based upon constant volume, it should do this. So it's confined on the sides and on the end, but one boundary of the reacting volume is moving. So it's not a constant volume problem. It's not a constant pressure problem. What is it? So typically the modelers will assume one or the other. They'll assume constant pressure, constant volume, and in many cases you get the same answer if you're only modeling it up to about here. But if you want to model what happens as the chemistry continues, there's no good way to do this. That's a modeling problem. And we're just kind of coming to grips with this. How can this process be modeled? We wrestled with this for a while, and there's different strategies you can use. You can use a very small amount of fuel so that there are hardly any changes. That means you can make your experiment nearly constant pressure. And you can get away with this by using very sensitive diagnostic techniques rather than crude diagnostic techniques. Or you can use this new idea we have. It's called constrained reaction volume. This idea is now maybe about 5 years old. And so we tried to make the experiment constant volume, and I couldn't figure out how to do that. And then we said, well, maybe we'll try to make it act like it's constant pressure. So we decided to, or this has now evolved over about 3 or 4 or 5 years, to modify the shock tube in another way. So here's our conventional shock tube. The entire test section is filled with reactive mixture. Imagine it's a reactive mixture, exothermic mixture. When the reflected shock goes back, the entire region can burn. The entire volume of gas can release energy. Well, the larger the amount of energy released, the larger the change in pressure. So how can we reduce the change in pressure? Well, let's constrain the reaction volume so that it's only down near the end. Kind of a simple idea once you think about it. Now once the incident shock is post-reflected shock, the reflected shock is here. This is a gas that has no combustible components. This is the only gas that can release energy. So we've limited the amount of energy release, and the pressure releases itself axially. This is the constant volume part on the sides, but this part is the moving boundary. So the idea is let's reduce the volume of reactive gases, thereby reduce the pressure change, and thereby make it close to constant pressure and make it something you can model. So you also can model it. You can go into ChemKin, which is the routine people use, and you can specify the initial condition. And you can, assuming that it's adiabatic, you can specify pressure versus time. One limit is the pressure is constant. So you can specify constant pressure, or you can specify the pressure, and then you can model it. And so this also has another benefit. In these shockwave experiments over here, if the shockwave has been slowing down, it turns out that the temperature over here is a little higher than it is right here, and this can burn first. And so you can sometimes get what's called remote ignition. You'd like to think that it burns near the edge first because it was heated first. But if that temperature is a little lower than this temperature, it might burn faster here, and that causes another problem. So this idea eliminates 2 big problems. Here's the conventional shock tube, hydrogen, oxygen. Here's this, it burns right there. Also, we had not solved the DPDT problem. Notice that the pressure is changing with time. Now, if we get used to this constrained reaction volume idea, you can't really tell the difference between in the pressure histories with and without combustion. You can see it in the emission. It's still burning, but you can't see it in pressure anymore. So that's, I think that's an interesting and valuable concept that we've come up with. So it allows, and why do I care? It means that we can model throughout the combustion. So not only can we measure by emission, the ignition delay time, we want to measure the continuing evolution of species. I think I'm going to show that. This is ethylene ignition. Okay, so now if we use a temperature sensor, which we measured by including some tracer of CO2, we can measure the temperature, and what you see is that the temperature agrees pretty well with this model called JetSurf. So if you remember from thermodynamics, for an adiabatic system, dH is VdP. So if the pressure changes 0, the enthalpy changes 0. But that's the sum of the sensible and the chemical enthalpy. So what's happening is that the total enthalpy is staying constant, but as the combustion takes place, the temperature is going up and the chemical enthalpy is going down. So we're actually measuring the predictable temperature change in this environment. So I think that's one of the latest advances in shock tube technology that I think will make a difference. Here's just just showing that if you do the ignition delay time for butane and air, if you do it the old way, you get this answer. If you do it the new way, you get this answer. The idea being that this one can be modeled more correctly than the old one. So we're gradually making experiments better and more amenable to modeling. And of course, what you see is that by doing it this way, we get a different answer, and it's always longer, mostly longer. So when people were using these data, they were adjusting the kinetic model to match the data, but by using the wrong gas dynamic model, they were achieving the wrong kinetic model. So again, the experiments are correct, but they've got to be modeled correctly. And part of that is the gas dynamics or the thermodynamic constraint that goes into this. It's not perfect. We still have problems to work on, but it makes a difference. And here's just another example of a low temperature butanol, showing you get a different answer when you do the experiments, the CRV way versus the old-fashioned way. If we use a model from Sarathi at KAUST, it agrees pretty well with the data there. Okay. CRV strategy yields longer times at low T than the conventional, and that has implications. So we're trying to push into the NTC region. We have to be sure our experiments are correct, or we'll reach the wrong conclusions. Okay. Where am I? I think I'm right on time. So that will set the stage for the next lecture, in which I'm going to show you how we attack elementary reactions and we use laser diagnostics. All right, any questions before we break? Yeah.
For your extended shock tube where you have the tube,
Yes.
do you account for any losses in the flow due to the flow change direction?
So first I wanted to make the shock tube longer, but the room's not longer. What do? I thought it was going to go up. No, I'm afraid it's going to fall over. So we decided, well, we'll just try it. And the fact is that yes, there's probably some issue around the corner, but we tried it and we could never find an effect. I think there's enough other effects that are at least as important. This U, which is, I don't know, the distance between center lines is probably about a couple feet. No, I don't see any evidence of it. There's some other issues that are, I think, more important than that one. What I'd really like would be a code that would tell me, well, first of all, a code that would tell me that effect. But as far as I can tell, there's no effect. What I'd really like is a code that would tell me what is the ideal diameter versus distance of a long tube. Recognizing that in the real shock tube, you're trying to compensate effects. And you're trying to I would like to change the geometry, the length and the diameter, to compensate for these other effects. And there is no such code. So we have to do a lot of this by trial and error.
Are those boundary layer effects that you're...
The boundary layer effect is why the incident shock wave slows down. The result of that slowing down is that we get non-constant reflected shock properties. We want constant properties. So we compensate by changing the area. That's fine for up to, say, 10 milliseconds. But now I want to get to 50 milliseconds. And I do that by continued length. And I don't have a code that allows me to decide exactly what to do. So we just try things. And I can see the potential, but we have to do a lot of trial and error work. And then there's questions about should you be changing the composition of there's a lot of higher order questions that we get into. So yeah, if the instant shock were at a constant speed, this would be a lot simpler, but it's not constant speed. It slows down due to boundary layer effects. Okay, any other question? Yeah.
When you were using like high levels of dilution for
Yes.
the pressure
Yes.
constant.
No, the high level of dilutions, if we use argon, gamma's 5/3, that you're going to have more nearly constant temperatures because you have a heat bath.
Oh, okay.
Also, gamma 5/3 eliminates another problem I haven't told you about called reflected shock wave bifurcation. So when reflected shock comes back, interacts with the sidewall boundary layer, there's another non-ideal effect, which potentially goes to 0 when you use gamma 5/3. So the best experiments are highly dilute argon.
Okay.
Then we can do clean experiments, but the practical people want you to do it in air.
Okay.
That's the problem. Practical people want you to do this in air.
But in
which-
that case, you cannot use longer like the pressure time histories in order to see where the ignition delay time is. So my question was for like using OH,
Yes.
you're using laser absorption or you're
Yeah, yeah.
maybe emission or
Yeah,
like chemical
yeah,
luminescence.
yeah.
Which one are you?
We do both.
Okay, gotcha.
But the point is, if the pressure's change, we don't like it if the pressure, we try to remove this. Because if the pressure's changing, the temperature's changing. It affects our spectroscopy, it affects the chemistry, it's not good.
Yeah, sure.
If you know exactly what it is, maybe you can account for it. Like in the RCM. People in the RCM deal with pressure versus time, temperature, they deal with it. But it's an approximation. Best approximation is remove the problem. Yeah.
For using the driver inserts to improve the constant pressure
Yeah.
time behavior, what's actually, can you just explain a little bit about what the mechanism is of how the
Sure.
driver insert
So you're basically reducing the area as a function of distance. When the expansion wave comes back into the driver, it first encounters this insert. You can do with an XT diagram, you can say, therefore, what will happen is that there will be expansion waves starting to come back. As the expansion is proceeding into the driver, it's sending back expansion waves because it's no longer a constant area, and they're proceeding at a known rate. First thing you do is you place the insert so that they begin to arrive when the reflected shock arrives. And the rate of expansion waves that you're producing has to compensate for the pressure rise. So it's basically just deciding where do you put it and what's the rate of change of the area, which means the rate of change of expansion waves that are running down the tube. That's the crude way to think about it. And we did it, there's a paper we did on this about 10 years ago, I guess. But it's very crude. I really wish I had a code that does this. I haven't been able to find a shock tube code that accounts for boundary layers and variable area. So we do a lot of trial and error stuff. But the effect is changing the area in the driver means that you begin to send back expansion waves because it's not a constant area. And you have to decide what is the rate of producing them and when do you want them to arrive. And then it'll work over, we can use this over a couple hundred degrees of operation. We don't have to change it every test. We have a few different configurations where it works. But it's facility specific. So if you have a small diameter tube, you're going to have higher attenuation rates. You're going to have to do it differently than my big diameter tubes. Bigger diameter tubes better, much better. Okay, any other questions before? Yeah.
In your experiments with the small portion reactive gas, how do you keep that from diffusing into the other?
Exactly.
gas?
Okay, so that's the
Have any
exactly. Yeah. Yes. Sure. So in our first generation, we did this the poor man's way. We filled the shock tube with the test gas. Then up by the diaphragm, we put in inert different gases that are non-reactive. And we move the interface down. So we move the interface so that it's down. The trouble is, as you do that, the interface starts to broaden by diffusion. And so you end up with a smaller and smaller sample of undiluted test gas. And so you might not be able to have a nice, clean, uniform volume. We solve that in two ways. First, we always measure with the laser exactly how much fuel we have in this experiment. So what we see is that as the instant shock comes by, we can tell what we have. So you have to do it in situ. The second thing is we realize that's not the best way to do this. So we spent a year building a sliding valve. So the best strategy is you put a valve, it's about 35 centimeters from the end, and we fill both sides equal pressure. Only this side has a reactive gas, and then we gently remove this separation. Then there's still a little diffusion that takes place, but it happens kind of slow, and we can characterize it. So you get close to the ideal. You have a known volume without diffusion, remove the barrier, a little bit of diffusion, but we minimize it, keep the time delay to maybe 5 seconds, and that's what we do. And then we also measure exactly what we have in real time with our laser. Yeah, that's a problem. And it was a bigger problem when we did what I call staged fill. That was our poor man's approach. But then we invested a year to build this sliding valve. So that's the best way. It's still an issue. But as long as you know, if you imagine that all you're doing is looking at a fixed sample of gas, I don't really care what's happening over there, as long as I measure what's happening here. So as long as I can achieve constant pressure and I know what the mixture is at the beginning, I'm okay. It doesn't actually have to be perfectly uniform. And if you keep the energy release down, you're not, the times are short enough, there's no real diffusion after the events begin. Okay, thanks. Okay, we'll resume in 10 minutes.